Hello and welcome to this edition of my Evotion Rhapsody video series. My name is Frank, I'm a passionate Rhapsody user, trainer and consultant and love to share knowledge to help you to become more effective. In previous videos I have shown why Rhapsody is the technological leader and so successful in the model-driven development domain of embedded applications with UML and full round-trip code generation. In this video I will further go into the technological details and concepts that form the basis for this. Then I will present the workflow of the two Rhapsody editions, Rhapsody Developer and Willard Embedded Studio, and explain how and why they are different. As mentioned, the valuable strengths of Rhapsody lies in the generation of platform-independent embedded real-time code from UML models, allowed to keep model and code always in sync. The special feature is that even abstract and incomplete models can already be executed on a real target. With this so-called rapid prototyping approach, experience and feedback with the application can be gathered at an early stage, which is groundbreaking for the further development and specifications. This seamless way of working between host and target contributes to the popularity of Rhapsody and allows early validation and feedback in innovation projects. Rhapsody supports a wide range of real-time operating system, RTOS, whether you use a general-purpose RTOS like VxWorks, Integrity, QNX, with or without multicore or hypervisors, up to small footprint RTOS like microCOS, RTX or Emboss, or even without any operating system, alias bare metal. The mindset, by which I mean the objective and values driving design decisions and way of working, differs depending on whether I'm developing for a general purpose operating system or for a resource-constrained microcontroller. While Rhapsody Developer traditionally supports the development of applications for general purpose operating systems, an extension of Rhapsody, the Willard Rhapsody Embedded Studio, is specialized for the development of applications on hardware-constrained environments. Simplified, it can be said, if you're developing a sophisticated mission control system based on a powerful microprocessor with a general-purpose operating system and rich middleware, you will most likely use the functional scope of the Rhapsody Developer. On the other hand, if you are developing a single-purpose controller application, like in a dishwasher, coffee machine or in cars, you will most likely use the Willard Embedded Studio, which is optimized for this purpose. For those who don't yet have Rhapsody, Willard Embedded Studio comes with a very cost-efficient Rhapsody OEM edition in a bundle. Let's get started with the core technology concepts of Rhapsody, which is common to both editions, and take a closer look at the technical concepts. How is it possible in Rhapsody to generate code for the most diverse environments from a UML model? On the one hand, we always have a processor on which your application will run at the end. In most cases, this is based on an RTOS. On the other side, we have the model. Most of the time it will be UML, but I see more and more customers using SysML and generating embedded code from these models in Rhapsody. Maybe you also have some existing legacy code that you want to continue to use. Nothing easier than this, you simply integrate it. And now it gets interesting. Between the generated code and the RTOS, there is a service layer, the Rhapsody framework. And this framework fulfills and serves, besides the platform independence, further the following purposes. Thus, it realizes the behavioral mechanisms and further UML concepts in the code. Example. In UML, objects communicate via messages. These messages can be, for example, events, which can trigger a state change and a reaction for the receiver. If several objects are to exchange messages with each other, a delivery mechanism and possibly a message queue are needed. And exactly these concepts are provided by the framework. As a developer, I can use these mechanisms and access simplified constructs for the inter-object communication. Without the framework, the implementation of activity diagrams and state charts would be much more time-consuming and involve a lot of manual work and thus added maintenance. Since a lot of functionality is outsourced in so-called framework classes, a lot of complexity is hidden, making your own application code much more readable and understandable. In order to be able to exchange messages, relationships to other objects are required. In UML, there are several concepts for this, from a simple point-to-point to one-to-many relationships, be it a composition, aggregation, association, or even qualified relationships. The realization of these concepts, for example, managing objects in a one-to-many relationship, is provided by the framework. One of the absolute highlights is when the generated code runs on the target, and the behavior can be tracked in the UML model on the development computer. The fast executability of even incomplete models, the graphical debugging of applications on UML level would not be possible in such an ease without the framework. One of the key points is the runtime abstraction. Below the framework lies the operating system abstraction layer, also known as operating system adapter. This abstracts common operating system services for the generated code. In simple terms, these are interface classes with virtual operations. The implementation, the adaptation, depends on the underlying operating system. So you can create a model once and then run it on different platforms. Keyword Platform Independent Model, PIM. In the simplest case, the framework is a precompiled library that is simply linked to the application. For this case, the question of certifiability always comes. It should be mentioned here that this code is also available, or even better, there is a UML model behind. Certification artifacts and documents are also available for the framework. As such, from a certification view, the same applies as if the code would have been manually written. For the last point, optimized workflow, I want to discuss this in more detail in the next slides. This differs slightly depending on whether I use Rhapsody Developer or Willard Embedded Studio. As mentioned, the workflow of Rhapsody Developer is optimized for the use of general-purpose operating systems, which are mostly based on microprocessors with memory management and enable dynamic loading and unload of application modules. All essential steps can be performed almost exclusively in Rhapsody, like modeling, writing implementation code, generating and compiling the application. To run the application on the target, you simply connect to the target in Rhapsody. In VxWorks, Rhapsody uses a target server, with Greenhills, the probe, and so forth. There are also other solutions such as integrating with the Lauterbach debugger. In my example for the Raspberry Pi, I use a simple TCP/IP connection. After the download, I can start the application and debug it graphically in Rhapsody. If I also want to debug the code, I use in parallel the target IDE of the manufacturer, Wind River Workbench or Multi, or in my example for Raspberry Pi, also like to use Visual Studio or Eclipse. Complex applications running on general-purpose operating systems were and are the original target market for Rhapsody. However, the majority of embedded software applications are simple applications, or better say single-purpose applications, running on smaller microcontrollers. After all, they account for 90% of the worldwide volume of microcontrollers. Willard specializes in this market and developed a Rhapsody edition in which the framework and the way of working is optimized for the development of such applications. When you build an application that has to run on a low-cost microcontroller, which also implies resource constraints, low memory, then the mindset and the approach is quite different. In this context, you're usually assembling the entire system to work together in one system image, containing application, RTOS, startup code, which is then flashed in a single system load. So there is no dynamic load and unload of applications, and you do not search for a soft reset. However, you absolutely have to know your processor, or you're lost. And there are thousands of these tiny little microcontrollers. Luckily for you, you may have a specialized target IDE, for example Keil, which allows you to easily select and configure your controller. And this is a step where the Willard edition differs. In the Willard edition of Rhapsody, the model is developed and the code is generated but not compiled. Instead, the Rhapsody Willard edition transfers the code via a so-called deployer into the target IDE. Of course, I can also edit the code in the IDE. The changes are synchronously transferred to the model in Rhapsody. In the target IDE, I compile the application, flash it and start it on the board. If I want to interact with the application on UML level, I can use the Willard target debugger. Let's have a look at this way of working in a demo. Here I use the Willard Rhapsody Embedded Studio. Looks like a Rhapsody? It is Rhapsody. The base behind is an extended Rhapsody Architect Edition. So I can perform my usual tasks: modeling, coding, tracing requirements, or generating documents. So things you usually do with Rhapsody. At component level, I can configure and select the environment. In this example, we have a couple of choices. If I now press Generate Make Run, the code is generated in the first step. Now comes a difference. The code is not compiled in Rhapsody, but the Willard deployer is activated, which transfers the source code and files into the target IDE. If the target IDE is not open, this is started at the same time. In the IDE, I can now compile the said single image and flash the board. All required files are part of the project to create the system image: RTOS, device driver, startup code, an optimized Rhapsody framework, the real-time execution framework, RxF, I will come to this later, and for sure the generated source files of the model. When I press build or rebuild, the whole system image gets compiled. When done, we can download, or better say flash, the image to the target. For this target I'm using JTAG. Then I simply start the debug session, which brings me to the first line in the main. Here I could further single step through the code, set breakpoints and so forth. For this demo I simply press Run. Now let's move to the Willard Embedded Studio. For debugging on UML level, I simply start the Willard Embedded UML Target Debugger. This connects to the target, in this case via the Keil API, through the existing target connection. We can now see the application runtime objects. As this application is waiting for some events to get started, let's inject some events into the application. I can select the event, then the receiving object, and press Inject Event, which will start the Blinky. Because I have two LEDs, let's start the second one as well. In the target debugger, I can track the interaction of the objects and see the elapsed time. Before I continue, I will stop the debugger. Alright, let's come to the great benefit of this integration. In the Keil IDE, I can elegantly select another hardware. Keil offers me a rich selection of endless supported devices and boards. Purely for demonstration purposes, I choose the Nucleus board from ST, which I got as a gift from ST at the Embedded World. So here some greetings to my friends at ST. When I select the device, Keil automatically pops up and says that my current board support package does no longer fit. That's okay. So let's select Nucleo. What's this? Okay, looks like I don't have the component. Don't mind. Uncheck this, so Keil guides me and I'm done. The LED should be fine. I have the right driver here. Okay, so let's build the new image again with the new sources. This kind of configuration is independent from Rhapsody and the UML model and will not change my model in Rhapsody, but guarantees me highest flexibility. If I make changes in the model, I simply generate the files again into the project. Okay, we are done. So let's flash the board. Start the debugger, launch the application, Press go again, go to the target debugger, inject events, and we're done. How cool is that? The Villette Embedded Studio is based on many years of know-how and optimizations for the development of application on resource-constrained environments. Thus, the Villette Embedded Studio comes with its own Rhapsody framework, the Real-Time Execution Framework, the RxF, which is optimized in terms of memory, energy consumption, and runtime. If the application is safety critical and needs to be certified, there is a further certification kit to support this. For the interaction with the target on UML level during the design and implementation phase, the RxF has implemented a minimalistic target monitor. Events can be sent via the Villette target debugger. This kind of debugging is also deterministic and can be used for model-driven testing. That's it for today. In my next video, Unboxing Villette Embedded Studio, I will show you how to get your own target up and running, from downloading the development environment's installation to running application on a microcontroller. So don't forget to subscribe today and please provide a like if you want to see more of these videos. Hope to see you soon. Thank you and goodbye.